Hello friends, welcome back to the video series on design of steel structural elements. So in this example we'll see how to find out the design axial capacity for built up type of columns. So now the problem is steel stanchion is also called as for a column, there is another name, is formed of two channels ISMC 350 placed back to back as shown in this figure with a spacing of 200 mm. Effective length of the channel is 6 meter, means the effective length of the column is 6 meter, and we need to find the safe axial load that the column can carry. Also we need to find the extra load the column can carry if two plates of 400 by 10 mm are welded to the channel flanges on each side. We'll see the second part later, but first we'll find for these two channels placed back to back with a spacing of 200 mm how much load they can carry, right? Okay, so I will just write the formula to find the value of design axial load. PD is equal to FCD into A. Okay, so A is actually the effective cross section area of both the channels together. So if I just look into the steel table for ISMC 350, so the area is 53.65 mm square for each channel. Since we have two channels, so 2 multiplied by 53.65 multiplied by 10 square, because I need to convert that centimeter square into millimeter square. So 2 into 53.65 10 square, so I'm getting 10730 mm square. So this is the effective cross section area of both the channels together. Now to find FCD, okay, I actually need two terms, that is two things, that is which buckling class it falls. First thing is the buckling class of the channel, right, and the second thing is KL by R. To find the buckling class, you actually need to open the steel table, sorry, IS 800 2007, and if you see here in the last but one row, channels, angles, T and solid sections all fall under buckling class C. So our channel falls under buckling class C, right? So next thing is I need to find the value of KL by R. So KL is actually, they have given that this term, the effective length of the channel is 6 meters, means they have actually given the value of KL, which is 6000 together divided by R minimum, right? Now this R minimum is actually calculated as minimum moment of inertia, okay, divided by the cross section area. Now how this minimum moment of inertia is defined? Before that, let me explain you these axes. These red color one are actually called the global axis, means the global XX and global YY, means they're actually the axis for the two channels together, and the axis shown in blue color are actually called the local axis, which are the axis for each and individual channel together. Now this capital G is the CG of these two channels together, and the small g's are the CGs of the individual channels. Okay, so now this I minimum is moment of inertia of this whole channel together, means it should be minimum of XX and minimum of YY, mean minimum moment of inertia of global XX axis, minimum moment of inertia of global YY axis. So I can write here it as minimum of IXX and IYY, whichever is minimum that I have to put. So this divided by A, that is the area of both the channels together. Now I need to find which axis is minimum and which axis is maximum, right? When there are two channels together, what happens here is, so IXX will be, that is global moment of inertia about XX axis, is nothing but 2 times the local moment of inertia about XX axis, and IYY, that is global moment of inertia about YY axis, is nothing but 2 times moment of inertia about YY axis plus area of each channel multiplied by the d square, right? Is d is this thing. So now this is actually minimum, will be minimum, and this will be always maximum, right? So out of these two, the local moment of inertia about xx axis is actually minimum, so that I have to use here. So I will just find out Ixx, which is nothing but 2 times the minimum moment of inertia about the local xx axis. So here for ISMC 350, I need to find the minimum moment of inertia about xx axis. So this is that, okay, column which gives me that value. So for ISMC 350, it is 1,008 centimeter square. It is given in centimeter square. It is 1,008 into 10 raised to 4. Because it is in centimeter square, I need to convert that into millimeter square. So it will be 2 times 1,008 e raised to 4. So I'm getting 200.16 into 10 raised to 6. millimeter raised to 4, right? So this will be minimum, that I will substitute here. So I will get R minimum as under the root 200.16 into 10 raised to 6 divided by the total area is 10730. So this I am getting 10730 under the root, so 136.58 I am getting. So R minimum I am getting 136.58. So I will substitute that value in KL by R, that is KL by R is equal to 6000 divided by 136.58. So it is 6000 divided by 136.58, which is 43.93. 43.93. So I need to go to table 9C to find out the appropriate FCD value for this KL by R. So I will go there, go to table 9C. Okay, so 43.94 lies in between 40 and 50. So for 40 it is 198. Okay, we'll just use that interpolation formula. So for 40 it is 198. Okay, I need for 43.93, and for 50 it is okay. So for 50 it is 183. So FCD for 43.93 I am getting 192.1. So for this I am getting FCD as 192.1 Newton per mm square. So now I can easily find the value of PD, which is 10730 is actually the effective cross section area multiplied by 192.1. So it is 10730 multiplied by 192.1, so which I am getting to be 2061.24 kilonewton. 24 kilonewton is the actual load carrying capacity of two channels ISMC 350 placed back to back at a spacing of 200 mm. Now in the second part of the problem, what they have asked is, if they place two plates of 400 mm by 10 mm thick, and if they are welded to the channel flanges on each side, so what will be the load carrying capacity, what extra load the column can take. Now the configuration will be something like this. Now these are the two channels placed back to back, same with the 200 spacing, and these are the two plates which are placed on each flanges and they are welded to the column. Now I need to find what is the load carrying capacity of this configuration, means how much extra load it can take, right? So I will just write once again the same formula to find the design axial capacity, that is PD is equal to FCD into A. Now A will change here because I have added two extra plates, so 10730 is the cross section area of two channels together plus, okay, 2 times, because two plates are there, 400 multiplied by 10. So this I am getting 10730 plus 2 times 400 multiplied by 10. So I am getting 18730, getting the value of 18730 millimeter square is the effective cross section area of this configuration, right? Now similarly I need to find the value of KL by R. So KL will remain same, which is 6000, right? And now I need to find the value of R minimum. Now once again R minimum I need to find. R minimum is actually minimum of global XX axis and global YY axis, right? So I will find the global XX and global YY axis, that is moment of inertia about global XX and global YY, so that I will come to know which one is minimum. So I will find IXX now. So IXX is 2 times, right? 2 times the IXX of single channel, so which is, we have written just now, 10008 into 10 raised to 4, right? Plus, now since two plates are added, that also I have to take. Now these plates are in a rectangular fashion, so moment of inertia for the rectangle is BD cube by 12. So this I will take. So B will be 400 and D will be 10, because B is the dimension which is parallel to the axis on which I am finding moment of inertia. So B will be 400. So it is 400 B D cube by 12 plus, okay, plus area of plate, that is 400 multiplied by 10, this multiplied by D. So D is actually distance from here up to here, right? So this is 350 and this total will be 350 plus 20, that is 370. This total is 370 and half is actually 185. So means actually it will be from here up to here. So this is actually 185. But I want distance from here up to here. So 185 minus 10 by 2, that is 5. So it will be 180. So it is 180 square. So this is actually from the parallel axis theorem, that is IG plus A into D square. That is, D is the definition of D, that is the definition of IG is moment of inertia about its own central axis, area multiplied by distance of CG of that shape up to the axis on which we are finding moment of inertia, right? So I will find out the value of IXX and tell you how much it will come. So 400 10 into 10 cube by 12 plus 400 into 10 into 180 square. So this whole thing multiplied by 2 plus 2 times 10008 e raised to 4. So I'm getting 468.96. into 10 raised to 6 millimeter raised to 4, right? Similarly, I will find IYY. It is 2 times IYY of single channel. IYY of single channel is 430.6. 430.6 into 10 raised to 4, right? Now here plus, that is Ig plus AD square, that is the area of one channel. Area of one channel is 53.65, that is 5365 multiplied by d square. Now d square is actually distance from here up to here, that is this distance. This I have marked here, that is d square. Now how will I find that one? So this distance will be actually given in steel table as the term, the given term is, right, you can see here it is given as CYY, right? So CYY for ISMC 350 is, so CYY is given here, right? Okay, next page it will be given. Okay, CYY. I think in the previous page itself they have given the value of CYY. Yeah, CYY is here, means this column I have to see. So CYY for ISMC 350 is 24.4 millimeters. So this distance is actually CYY, which is 24.4 millimeters, plus this distance is 100, because this total distance is 200, so 100. So 100 plus 24.44, so D is 124.4 square. Similarly, it is once again Ig plus A into D square, right? So why multiplied by 2? Because 2 channels are there. Now plus this is for the channel, plus for the plates, right? So I will multiply it by 2 once again, because 2 plates are there. Now B will be 10 and D will be 400, because 10 is the dimension which is parallel to the axis on which I am finding moment of inertia. So it will be 10 multiplied by 400 cube by 12, plus area is 400 multiplied by 10 multiplied by D. D is actually now distance of CG of this rectangle up to y axis. Now you can see that the CG of rectangle, that is 400 mm by 10 mm, lies on y axis itself. So there is no distance between them. So it will be 0. So if I calculate the value of IYY, so let me check how much it will come. So 410 into 400 cube by 12, okay, this multiplied by 2 plus 2 times 430.6 e raised to 4, 430.6 e raised to 4 plus 5365 multiplied by 124.4 square, 4 square. So I'm getting 281.32 into 10 raised to 6. So out of IXX and IYY, so IYY I am getting minimum, so that I have to substitute in finding R minimum. So this will be now 281.32 into 10 raised to 6 divided by the total area, which is coming out to be 18730. So 281.3 e raised to 6 divided by 18730. So I am getting 122.55. 122.55. okay. So now R minimum is 122.55. so I will find out the value of KL by R. So KL is actually 6000 divided by 122.58. so 6000 divided by 122.58, so it is 48.94. So once again it lies in between this only, so I will just write here 48.94. so I am getting FCD as 184.6. Newton per mm square. Therefore PD is equal to 18730, that is AE multiplied by 184.6. so 18730 multiplied by 184.6, so I'm getting 3457.55 kilonewton, right? Now you compare this load with the previous load, which was 2061.24, right? So the extra load that it will carry is is 3457.55 minus 2061.24. So 3457.55 minus 2061.24. so the extra load carried is 1396. .31 kilonewtons. So this is the extra load it can be carried. Also here actually they had asked the safe load, okay. In the first case, that is a safe load. Safe load, it is very easy to calculate. It is nothing but 2061.24 divided by 1.5. So it is 2061.24 divided by 1.5, so which is 1374.16. You can say 1374 kilonewtons. This is the safe load. Right, now you can see here with the addition of plates, the load carrying capacity has increased as compared to without plates. So this is how it can be solved. I hope you understood. We'll see some more videos in the next. Right, thank you, bye.